All right, how's everyone feeling today?
Tired.
All valid. To all who say tired, I hope that the weekend is very restful. Main thing for today is we're going to continue talking about rotation. Does anyone have any questions, needs, etc. before we get started? All right. Let's see. Last we left off, we had begun looking at rotational motion. I'd like to very briefly review that information because it is new and I want to make sure that it's still in your brain before we move forward. We began describing rotational motion because it requires a different mode of thinking than linear motion. When something is rotating, we don't think of how many meters forward it moves, we think about how much it has spun, which we measure with angular displacement. Wow, I forgot my own word for a second there. Angular displacement measured in units like radians, degrees, or rotations instead of meters. And I'll put the conversions for that back on the board. One rotation. The same thing as saying 360 degrees. The same thing as saying 2 pi radians. And when something is spinning, rather than describing its linear velocity in meters per second, we describe it with its angular velocity in units akin to radians per second, rotations per second, degrees per second, commenting on how much it spins every moment, rather than how far forward it moves. We looked at a couple examples utilizing these. Today we are going to continue looking at various forms of rotational motion and also how it relates back to linear motion. Because, I believe I mentioned this, all of the ways that we've been thinking about linear motion, all of the relationships between the various aspects of linear motion, all of that logic still applies to the rotational world. We're not going to cover all of these rotational topics. I just kind of want to show you this to illustrate a point. Everything that we've done linearly, all that same logic still works angularly. All those linear formulas over there have what I would say angular counterparts, where you basically just switch the linear concept for the angular counterpart of it, and you're thinking in terms of, you know, radians spun instead of meters forward. We've already looked at the relationship between displacement, velocity. There is also such a thing as angular acceleration, which works the same as linear acceleration, where the velocity is just changing with time. All the same principles still apply. All the same relationships between these concepts still apply. We're just kind of expanding the way that we use them is my goal here. Trying to use the old logic to apply to a new situation. Does that sound okay so far? All right. And I feel like it's important to understand this similarity. I'm going to tab forward in the notes real quick to focus on the two things we talked about, the two things we're focusing on for right now. It's important to understand the similarities between the two types of motion because they are capable of happening at the same time. For most of this class, you know, start of semester until now, we've been looking at just linear motion by itself for the most part. Things have been rolling, but we've kind of been ignoring that part. We've just been looking at, you know, the delta x and the v in a straight line, the velocity and speed in a straight line. And it is possible for something to be moving forwards without spinning. Again, that's kind of how we've been viewing most things throughout the entire class. It's also possible as we described on Wednesday, for something to spin while not moving forward. And this is why this creates the necessity for describing rotational motion by itself. But, as evidenced by one of mankind's earliest inventions, it is also very likely for both rotation and linear motion to happen simultaneously. That's what rolling forwards is. This thing spins while also moving forward within the x-plane. The two can happen simultaneously, and one part is directly tied to the other. It's not just two things that coincidentally happen at the same time. In the case of a rolling wheel, the linear motion and the angular motion are connected directly. To try to demonstrate that, I'm going to take this wheel again. I'm going to roll it across my table. I want you to again notice the point you should focus on to confirm whether or not this thing has gone through a full rotation or not, I think should be the air valve here, because it's the only distinguishing feature on this thing. But I'm going to put my hand behind it and make it a little more visible so you can track either the valve or the position of my hand. And I'm going to take this wheel through one full rotation. So starting from here at 12 o'clock, rotating around, off the edge, and then we've gone through one full rotation. The valve and my hand are back at 12 o'clock. That is the distance that this wheel rolls in one rotation. If I want to roll further, if I want my delta x to increase, I have to keep spinning forward, correct? The two are tied to each other. If that is the distance one rotation takes me, this wheel can't possibly extend that to go further in a single rotation. This indicates that the linear displacement and the angular displacement are tied together. It takes a certain number of spins to move a certain distance forward. Does that make sense? And the amount of spins is actually going to depend on the size of the wheel. Because to demonstrate that, now park this wheel right about here where it landed. I'm going to take a much smaller round object, namely this golf ball. And it's going to be a little bit harder to see if you're in the back. I apologize for that. Try to get some of this stuff out of the way. This golf ball has a black line printed on it, and I'm going to kind of use that to indicate the starting position, like the valve on the wheel. So I'm going to start in the same position with that black line on the top. And I'm just going to rotate this thing one time, one full rotation, 360 degrees, and see how far it goes before that black line is back on top again. So one full rotation, and we're done. That was already 360 degrees. If it needs to go further, it has to spin more times. But one full rotation meant something different for each of these two round objects, correct? One rotation only takes the golf ball like 5 inches, whereas it took the wheel at least about 2 yards. So not only is the rotational motion and linear motion connected, the relationship between the two varies based on the object. One full rotation did not translate to the same amount of linear distance moved for each of these two objects. What is the difference between these two things that creates this difference? It's not a trick. If you think it's the obvious answer, you can say it. What is the difference between these two things? Size. Physically, the wheel is larger, and that correlates to one rotation carrying it further. Because the wheel has a bigger radius, again, I'm flashing back to geometry class a lot in this chapter. Because the wheel has a bigger radius, its outer edge has a bigger circumference. And that means it's able to move a further distance forward in a single rotation. Because physically the edge of its tire is longer if you were to rip the tire off and just lay it out as a straight line. And so that is what these formulas in the middle here are meant to represent. These formulas allow you to factor in the relationship between a single object's linear and angular motion based on the radius of the spinning object. That's what the R is in those formulas. The bigger the wheel, the more distance it covers in a single rotation. Smaller the wheel, the less distance it covers in a single rotation. And that's why, if you ever played with like Hot Wheels cars, those things' tires have to spin 8 million times to go anywhere. Whereas the wheels on a monster truck or a giant tractor tend to rotate pretty slowly because they don't have to spin all that much to go the same distance. So, for a rolling object, its linear motion and its angular motion are connected and happening simultaneously, and the relationship between the two depends on the radius of the item. These middle formulas here, labeled as the translation formulas on your formula sheet, they're listed in this column here, literally sandwiched between the linear column and the angular column. They are designed to kind of be like the bridge between the two, the portal between the normal universe and the evil rotating universe. Again, these are designed to take the linear thing and allow you to convert it into its angular counterpart based on the size of the item, based on the radius of the item. So just to finally read the formulas themselves out loud, delta x equals wheel radius times delta theta, and linear velocity equals wheel radius times angular velocity. You can use those to convert a wheel's linear and angular data back and forth. The one catch to these formulas, as convenient as they are for looking at the motion of a wheel, the one catch to these formulas is they require the use of radians as your rotational degree unit of choice. These formulas don't work if you plug in degrees or rotations. They require radians, and that's because the definition of a radian is kind of based in the formula for calculating the circumference of a tire, literally 2 pi r. That's why there's 2 pi radians in one rotation. So that's a big asterisk that you can put on these in your notes. You have to use radians for these. It might be the least fun, least, what's the word I'm looking for? It might not be the unit of rotation you think of the most, but it's the one these formulas require if and when you need to use them. Questions so far? All right. I'm going to put these up on the board real quick so that you have them when I tab away. And let's get a tiny bit of practice in for this. Two cars, very different size wheels. We're going to look at a sedan whose wheels have a 25 centimeter radius. That is already the radius, that is already the distance from center to edge. It is not the diameter, it's already a radius. The tires of the sedan have a 25 centimeter radius, and the truck has tires with a 50 centimeter radius. It's a very, very big truck. Both vehicles drive down the freeway at the same linear speed of 30 meters per second. R1 is 25 centimeters, R2 is 50 centimeters. Linear velocity, so normal, linear velocity, normal English letter V, is 30 meters per second. Both vehicles share that. Both vehicles are proceeding forwards at the same linear speed on the freeway. But they have very different sized wheels. And so their wheels might not necessarily be spinning at the same rate, even though the vehicle's bodies are still moving forwards at the same rate. And so, what I would like you guys to calculate for me is first, the angular speed of each vehicle's tires, and then how many times each wheel's tires spin in 1 minute at the above calculated angular speeds. Also make sure that this formula is on the board as well. So, given that information and the formulas we've been talking about today and Wednesday, give you guys a couple seconds to ponder and calculate either on your own or working with each other the angular speed of each vehicle's wheels and basically the wheel's rotations per minute. How many times each vehicle's tires will spin in 1 minute. How are we feeling on the angular speed, the rotational speed of each vehicle's wheels? Thoughts, concerns, answers?
Wait, what did you ask for?
The the rotational speed of each vehicle's tires. Now we know how fast the vehicle as a whole is moving forward, and that does include the wheels. Like the wheels would have to move forward at the same speed. And we separately know the radius of each vehicle's tires. This should allow us, using the new translation formula from the other slide, allow us to convert the linear speed of the vehicle into the angular speed of its wheels based on the size of those wheels. And in general, the bigger the wheel, the fewer times it needs to spin. So going into this, we should get a smaller rotational speed for the bigger tire. It does not need to spin as fast to get the truck to move forward at the same rate as the car. Before I show the math, does that make sense? All right, so this is the new formula that will allow us to turn the linear velocity into angular velocity. Since we've got two vehicles, I've got it here twice. We just have to factor in the two different tire radii. Radii is the plural of radius. So we got here 30 equals R1 times omega 1. I've just decided the car is 1, the truck is 2. I have to plug in the radius of the car's tires. We do prefer meters around here, and since the velocity we're plugging in is in meters per second, we want to use meters for our radius to make sure that those two things are equal and cancel out correctly. So how many meters is 25 centimeters? Almost. It's 100 is the difference between base and centi. That would only end up being 0.25. Again, if you want to use the visual method to do that, centi to base, you would leapfrog the decimal point 2 places to the left. So from 25 to 0.25. And same kind of thing with the 50 centimeters as well. That would become 0.50. That should give us, if you then divide by 0.25 and 0.5 to get our two angular speeds, the car's wheels will be rotating at a rate of 120 radians per second. Again, that is the limitation on this formula. It will always give you radians, and you'll always have to plug in radians. And the truck's wheels, since they are twice the size, only need to spin half as fast. How's this first part feel? So again, the main takeaway here is the bigger the spinning object is, the fewer times it needs to spin to generate the same linear speed as a smaller object. Alternatively, the fewer times it has to spin to go the same distance as a smaller object. Now, the second part is determining how many times the wheels spin in a minute. Basically, what would the car's RPM meter be saying, rotations per minute? And since we've already got the angular speed of both vehicles here in radians per second, my thought would just be to convert radians per second into rotations per minute. Because those are both different measurements of angular speeds. We just want to convert from one to the other. Starting with the sedan, 120 rad per second. There is, as written over here, 2 pi radians in a single rotation. So if I want to cancel out radians and replace it with rotations, I'm going to put 2 pi rad on the bottom and 1 rot on the top. That'll cancel out the radians. And then we want to replace seconds with minutes. Seconds is on the bottom. So I'm going to put 60 seconds on the top and 1 minute on the bottom. So 120 divided by 2 pi and then separately times 60 will tell you the number of times the sedan's wheels are going to spin in a single minute. So converting from radians to rotations, and then converting from seconds to minutes. And that would be 60 over pi, 360 over pi. The truck would be the same conversion, just starting with 60 instead of 120. So, what are the rotations per minute of each vehicle? For the sedan, please let me know if your math disagrees. I've got 1,146 when you round up rotations per minute. For the truck, 573 rounding up rotations per minute. Again, since the truck tire is twice as big, it only has to spin half as fast. How you guys feel?
That's the third formula? Like the W...
This?
Yeah.
This is just a conversion.
Okay.
This is just me attempting to take the radians per second that this formula gives you and turning it into rotations per minute. Because the last question is, how many times does each vehicle's tires spin in 1 minute? So, number of spins per minute. Bless you. This is just supposed to be a conversion. The first part here is multiplying by 1 over 2 pi to turn radians into rotations, and then multiplying by 60 to turn seconds into minutes. Does that help? Okay. And it's the same conversion here for both parts, just taking the two different angular speeds and finding the two different number of rotations per minute. Yes?
Okay, I'm still a little bit confused about like why you chose that original formula. The V equals...
Over here?
Yeah.
The purpose of this formula is to allow you to convert linear speed into angular speed or vice versa.
Okay.
We know the linear speed of the two vehicles. They are both moving down the interstate at 30 meters per second forwards, and that includes their tires. I want to make that clear. Every part of the vehicle, whether it's spinning or not, has this linear speed. Now, in order for the car to do that, each of its wheels has to be spinning at a certain rate. And the purpose of this formula is to convert the linear speed of that vehicle into the angular speed of its wheels, depending on how big its wheels are.
Okay.
So this part here, it's this formula, a linear speed of 30, and then the radius of the sedan's tires, just converted from centimeters to meters. And so this omega 1 is the sedan's wheels angular speed, and this is for the truck. The only difference being it has bigger tires. You guys feeling all right? Did I answer the question? I will again fully admit the rotation stuff is weird. It took me time for it, as a physics major, it took me time to be able to wrap my head around it. So if you have questions, it just takes a minute, totally valid. Anything else on your minds right now? All right. So everything so far has been about how we describe and measure the rotational motion itself. We've got the amount that something spins, the speed at which it's spinning, and how we can relate that back to the linear world if something happens to be spinning and moving forwards at the same time. With those variables defined, I want to start looking at some specific forms and specific applications of rotational motion. Some specific interesting places where it occurs in the world around us and how that affects our world. Because knowing the rotations per minute of a car's tires might only matter to you if you are a motor enthusiast. But there are other places where rotation occurs in our lives that you can't escape, whatever your particular interests are. So that is, again, my goal. I want to show you guys where all this stuff matters to you. And the first place that it matters is pictured here. There is something common between all three of these photos here. I want you to see if you guys can figure it out before I explain it. There is something common happening in all of these scenarios. The first picture is a can being swung from the end of a rope, so just being swung in a circle above this person's head. Secondly, we have the moon orbiting planet Earth. And lastly, we have a bunch of cars just constantly driving and turning in a circle. I want to think for a second about what is common between all of these cases. And while you do that, I need to go find something that I forgot to grab out of the physics closet earlier. What do you think? What's in common across all three of these?
They're all rotating on an axis.
They all do feature something spinning about an axis. That is very good. Now, in each of these cases, I want to quickly identify what is spinning in each case and what it is spinning around. In this first case, the can is spinning around this point, the end of the rope being held in this person's hand. So the can is spinning around that fixed point. In this case, we've got the moon, and it is rotating around the center of the Earth. And then in this case, all of these cars are going to constantly be looping around whatever the center of this gravel dirt area is. So all of these scenarios feature an object spinning around some other point, some point that is not a part of that item. My next question, kind of asking a few leading questions here. Do you think that each of these items would normally be doing something like this? Do items normally, by themselves, start turning around a fixed point outside of themselves? No. In fact, Newton's laws very specifically tell us that most things just want to move in a straight line forever. They either don't move at all, or they move in a straight line. These aren't straight lines. These items are all being forced to do this by a literal force. In each of these cases, some force is causing the items to turn to constantly circle around a fixed point. In this case, it's the force of tension in this string. If the rope just snapped, the can would take off in a straight line. So it's the tension in the rope that is forcing the can to do this. It's kind of acting as a literal leash. Same as if you tied a lawnmower to a stake in the ground and let it constantly spin and try to mow your yard without actually mowing your yard. In this case, what is causing the moon to orbit the Earth? Gravity, the literal force of gravity between the two. If gravity didn't exist, the moon would rocket away in a straight line, which would be bad for us for several reasons. And then in this case, what makes cars turn is a little bit more complex. It's kind of a complex combination of both friction and the angle your tires are applying force to the road. But it happens because the tires have been turned. If you had the steering wheel straight on and the force was being applied in a straight line to the road, you wouldn't be turning. You have to turn the wheel, turn the tires, and that changes the direction that the force is being applied to the road. That changes the direction the force is acting on the car. If it weren't for those forces, these objects wouldn't be doing this. So even though rotational motion is everywhere, you will encounter it in your life. There's constantly things spinning because you encounter a lot of wheels on a day-to-day basis. Spinning actually isn't necessarily natural. It happens all the time, but it's not most items' innate tendency to do so. Most items have to be forced to rotate, specifically orbiting in this case. And in all of these scenarios, I've been saying what my slides are going to read in a minute. Some real force has to play the part of making all this stuff happen. And there's a certain name for that type of force, and I'm hoping it's a name you've heard before. That is called centripetal force. Sound familiar, I hope? Mixed reaction, okay. Oh man, my formatting's off. As much as rotation happens all around us in our daily life, most things don't want to spin. They want to move in straight lines. Newton's laws literally tell us this. In order to make something start spinning around a fixed point, you have to apply a literal amount of centripetal force in order to make that happen. And if you haven't heard the word centripetal before, this word is a fancy way of saying center seeking. The root word centri is center, the root word petal is seeking. So the centripetal force is a center seeking force. These forces literally pull items towards the center of the thing that they are spinning around. And that is what forces them to maintain that circular pattern rather than moving in a straight line like they want to. In all of those pictures from a second ago, there is a force that is constantly pulling the rotating item towards the center of its orbital pattern. So real quick, item, center, circle, force drawing the item towards that center. And that was true in all of those images. In the case of the can and the string, which I will replicate now with this thing, this is a rubber cork tied to a force gauge. And I can make this spin over my head, much like the can in the previous picture. The tension in this string is constantly pulling the cork towards my hand, and that's just because tension always has to act inward. There's no such thing as an outward pointing tension. The rope has to pull in on both sides by definition of what a rope is. So wherever the cork is and wherever my hand is, the string is always pulling the cork towards my hand, because the string has to pull inwards along its own length. So here, the cork is pulling leftward towards my hand, and as it spins around, the string still has to pull inward, so now it's pulling to the right. The rope always pulls inward on the cork, even if the direction that translates to keeps changing. So as the rope keeps spinning, the centripetal, the tension in the rope, which acts as a centripetal force, keeps changing direction to keep pulling the cork towards my hand. Same is true of the moon orbiting the Earth. The gravity between the moon and the Earth is always pulling the moon towards Earth's core, because that's the center of Earth's gravitational effect. Earth's gravity pulls everything towards its core. If you had a hole deep enough, you could fall in it towards the core, and then you would stop, because you'd be at the end. You'd also melt and be compressed to the size of a volleyball. Actually, more like a soda can. And in the case of the cars, again, when you turn the wheel of your vehicle, you are changing the direction of where the force is applied to the road, such that some of it is always pointing inwards towards the center of your turn. It turns out when you are turning in a car, even if it's just a 90-degree left turn, that 90 degrees is just part of a circle. You enter it here, and then you straighten the wheel out here and go back to normal. So when you are turning your car, you are just doing part of a giant donut. And again, the force in this case would be the changed direction of force between your car and the road. So there's always a force drawing the item towards the center of the point that it is spinning around. And that force is required to keep it spinning. Because again, Newton's first law says that the vehicle, whatever object, would normally move in a straight line were it not for this force. And so what this force is constantly doing is causing the item to centripetally accelerate and constantly change direction around the point it is orbiting. Because remember, acceleration means any change in velocity, and that includes changing direction. So basically, these things are constantly just changing direction so that they don't get any further away from the thing they're spinning around. If you kind of use the rope again as a literal example of that, dang it, tied myself in a knot. If something is tied to a rope, it physically can't get any further from my hand than this. It's constantly staying at the same distance from my hand, constantly changing direction to keep moving, but staying at the same distance. It can't get any further away, so it can't like pull out this way. All it's able to do is move to the side and keep changing direction, staying at the same distance, forming a circle. So some real force always has to play the part of this to cause something to spin. How you guys feel so far? All right. And you feel forces like this all the time. When you're in a car and the car starts turning, the car literally has to force you to turn along with it. And that's why you need to be seatbelted into your seat, so that the seat can exert force on you and keep you spinning along with the vehicle. And so when you feel forces when in a turning vehicle, that's why. Literally the car is exerting a force on you to keep you within it, keep you in your seat, and cause you to orbit along with it. So, whenever something is rotating around some other point, it is because there is some force acting as a centripetal force, causing centripetal acceleration. We have a couple new formulas for that. I'm just going to introduce them since we're kind of at the end of the lecture here. There's supposed to be a letter C in there. Centripetal force equals mass times centripetal acceleration. Centripetal force causes centripetal acceleration. And an object's current centripetal acceleration depends on its linear velocity squared divided by the radius of the circle it is creating. Alternatively, there's a second formula, angular speed squared times r, that will give you the same answer as long as you're using radians. I'm doing it like this. So, this is centripetal acceleration. This is what causes centripetal acceleration. And we will continue discussing how that works and why it matters to you next week. Questions, concerns? All right. Do please have a good weekend. Do let me know if you need anything or have any questions as you're looking over notes or doing homework. And please have a wonderful weekend.
Yeah, so now I feel like I have to give this. What?